keep in mind so now I want to like shift your attention to, instead of how I generated the plot, like what's actually in the plot. This is an illustration of the fake data that we're working with, right? And keep in mind that there's these clusters of points, and that on the small side, most of the points are scruffy, and on the big side, most of them are fluffy. And this is going to be relevant to interpreting the regression results that we see later. I'm going to show you this picture again with some lines on it, illustrating regression slopes, but I'm showing it without those lines now to get you thinking about what those slopes mean before I draw them on. What I'm going to do is fit 3 different regression models to illustrate what is happening when you fit a linear regression model. There are more options than 3 here for how to model Borks on the basis of the other information that we have, but I'm just choosing 3 for the sake of example. And the first one is the simplest one. I call it size only. And Borks is the response variable and size is the only predictor variable. I'm not controlling or adjusting for the type of fur that the dog has. The next model I'm going to talk about, I'll show you the results of these models in a minute. I just want you to preview what they are actually going to be. The next one I'm calling main effects. It models Borks on the basis of size and fur additively. So there's a main effect of size and a main effect of fur, and that's it, no interaction. So this is like, I will get the relationship between size and Borks adjusting for fur, or controlling for fur, as people sometimes like to say, and the relationship between fur and Borks adjusting for size. This is like, if size was the main thing I was interested in, this would be like adding fur as a covariate, or including them both in a regression model. These are all different ways of thinking about what I'm doing here.
Does the order matter?
No.
Okay.
And then the third model is the interaction model, and it models Borks on the basis of size and fur, and the size by fur interaction. So it just adds one more term beyond the main effects model. The asterisk in R includes both lower order terms and the interaction term, and we'll see that in the output in a minute. So now I want you to practice interpreting them. So I'm going to print the output of each one of them to the console here. Someone who wants to should give me a practice interpretation of the information contained, let's say the information contained in this regression table, generally speaking. And it's okay, also I'll leave the picture there in case you want to refer to that, but you don't have to refer to the picture if you don't want to.
I have a clarification question, which I think I know the answer to looking at the picture, but I just want to confirm, when you do a factor like this, and you see it says size big for that intercept, that's saying that big is the comparison group, right? Like what would be coded as?
Size big is, size is the name of the factor, and big is the name of the value coded as 1 in this variable.
Okay.
So this is a variable that has small as 0 and big as 1.
Okay, thank you.
Does it always tell you the variable that's coded as 1 if you don't like specify otherwise?
What it actually prints there is the name of the contrast. And whoops. When you convert something to a factor in R, it automatically generates a matrix of contrasts for you by default. These are the names of the actual levels of the factor, small and big. And this is the name of the contrast that it generated, which is by default coded so that small is 0 and big is 1. I could change this name. When you do relevel, it replaces the contrast matrix with a new one. But you can also replace the contrast matrix yourself by generating a matrix with whatever labels you want in the columns and assigning it to this. I retrieved the value of this object, but I also can assign over the value of this object with new contrast. Maybe that's a topic for another time, but the point is, by default, R generates indicator variables, dummy variables, that are 0 for all of the levels of the factor except for 1, and 1 for a specific level of the factor, and they name the indicator variable after the specific level that is 1. So in this case, it's binary, so there's only one indicator. But if it had multiple categories, then there would be k-1 indicators, each of them named after one of the categories other than the reference category.
Right, okay, right. So when you look at the estimate for this, it's showing you, is it showing you like the change when you would move from small to big? Is that what it's telling you? Or what's exactly like the value of 6.875 showing for the contrast?
Yeah, you can think of it as it's the difference between small and big. The difference in what?
Per unit change in X, it's the difference in Y, right?
It's the
Yeah.
difference in the fitted value of Y per unit change in X, yeah, or the expected value of Y, or the average value of Y, depending on what your variables are. And in this case, a unit change in X is what?
From 0 to 1, so just 1.
Yeah, and well, big is 1 and small is 0, so it's just the difference between big and small. So 6.875 is...
My mind always tries to think of this in terms of continuous, but it only goes from small to big. So is 6.875 like the average fitted Y, or like the average change in the fitted Y when you go from like a small dog to a big dog? Is that a way to think of it?
That is a way to think of it. The way I would probably say it is it's how much bigger is the average for the big dogs compared to the small dogs.
Oh, okay, that makes sense.
So what is this one, 32.2?
I remember learning that your intercept is like your base reference category, right?
The intercept is the value of the fitted value when all the other variables are 0.
Right. Okay.
Which in this case, since we're talking about a single categorical variable, you can think of it as the average value for the reference category.
Okay.
So the average value for small dogs?
Yep, exactly. So this 32.247 is just the mean for small dogs.
Okay, so if that's the mean for small dogs and big dogs bark more than small dog, is it like on average 7 barks more than 32? So it's like their average is gonna be 32 plus 6.8.
Yeah, about 39. Yeah.
This is so in the beginning I was like, I think I know what the reference group is, because the plot right here is so misleading, because you think that all those high numbers for the small dog are going to drive that average up. I guess I'm really not good at looking at data like this.
That's why I called attention to there's a lot of points down here.
Yeah.
A lot of small scruffy dogs and a lot of big fluffy dogs. So the average Borks for the big dogs is higher than the average Borks for the small dogs by 6.8. And that is a positive slope, right? I mean, so the big dogs are higher, and it's statistically significant by whatever measure of statistical significance you would be using. So the big dogs Bork significantly more than the small dogs on average in this example.